Behind me, I have an alternating sum of squares. So we have minus and then plus and then minus and then plus and then so on and so forth until we have plus and then minus, 51 squared. So how do we evaluate this? Well, if it was just a sum, like a direct sum without any minus signs, it wouldn't be too bad. We could use the sum of squares formula partially. However, this one, it's not going to cut it. So what do we do? Well, this one's actually really easy to evaluate if you are familiar with a certain identity. The way that we factor something of the form a squared minus b squared is just equal to a plus b times a minus b. And here is the key idea. The a minus b part over here, if you were to focus on this part and focus on grouping these terms as I'm underlining like this, notice that the a minus b part is just constant. It's just negative 2. 1 minus 3, negative 2, 5 minus 7, negative 2. And from here, you probably have an idea of how to do this already, now that I've told you. However, I'm still going to execute it. So, if we were to factor this part with the difference of squares, we would get, so I'm going to first write the a minus b part. That would be 1 minus 3, so that's negative 2. And then we have 1 plus 3 by the formula, right? By the identity. Now, because the next part is also quite similar, it would be negative 2 times 5 plus 7 this time, right? And you can imagine this just goes on. And when we arrive at this, we would get, again, 49 minus 51. That's still negative 2 times 49 plus 51. So this is basically equal to this, right, by the factorization. And now we can just bring out a negative 2. If we bring that out, we would get negative 2 times, well, this isn't hard to evaluate now. 1 plus 3 plus 5 plus 7 plus, all the way until 49 plus 51. This sum really isn't that bad because we can evaluate it like this. First, still write the negative 2 at the front. And this sum has a very special way of evaluating it. Consider this, 51 plus 1. Well, that's the same as 49 plus 3. And you'll notice that the pairwise sums are always equal. So the pairs are always 52, right? And we just need to multiply this by the number of pairs that we see in this sum. Well, to get that, we need to get the number of terms in this sum and then divide it by 2. That's the number of pairs. The number of pairs in this sum would be equal to 51 minus 1, so that'd be 50. However, we are counting by 2's, right? We're skipping by 2's every time. So we divide that by 2. However, when you use this method, you are actually undercounting by 1. Think about why if you're not familiar. So adding by 1, we have 26 terms in the sum, it turns out. So it means that we have 13 pairs. And there you go. Now you can calculate this by hand pretty easily, or punch it into a simple calculator, and you would get negative 1352. And that is our answer. Now, even though this particular example wasn't that hard, now that you've seen this video, I challenge you to do this. If I were to cross off this last part and instead replace it with plus or minus n squared, can you derive a general formula for this sum? And over here, we can see that whenever n is congruent to 1 mod 4, we have a plus, right? Otherwise, if it was congruent to instead 3, then we have a minus, right? Based on the pattern that we're observing. So, can you derive a general formula? So that's going to be it for this video. I don't know about you, but short videos have always been very helpful for me. So if you found this video interesting and if you learned something new from it, then please do consider subscribing and dropping a like. Thank you.